फाइन सर, आशीर्वाद है सर आपका।
That's today is the last day, ना?
यस सर, यस।
Yeah. Okay. कैसा रहा ओवरऑल? Good.
सर बढ़िया रहा सर, और आपके लेक्चर के बाद और बढ़िया हो जाएगा सर। क्योंकि सर बहुत से पार्टिसिपेंट्स अर्थक्वेक से रिलेटेड चीजें ज्यादा जानना चाह रहे थे।
हाँ, राइट
जी, तो आज का सेशन उनके लिए ही है।
हाँ, राइट है
जी
और ये कम्युनिकेशन विल बी इन इंग्लिश और इन
सर इंग्लिश
mixed
रहेगा।
हाँ।
इंग्लिश रहेगा तो अच्छा रहेगा, क्योंकि
Fine.
ज्यादातर साउथ से हैं।
हाँ, fine, that's fine. Yeah.
यस
Yeah.
So sir, on behalf of Civil IPSA family, I welcome you.
Thank you.
And sir, we are honored that you are coming here to deliver a lecture for us. Sir, shall we start the proceeding?
Yeah, we'll start. Yeah.
So now I request Professor Richa to give a brief introduction of Sanghvi sir.
A very good morning to one and all present here. Today, we are here on last day of our FDP with Major Dr. C.S. Sanghvi sir. Sir is working as professor and has 27 years of experience. Has done BE in Civil Engineering, ME in Structure, and PhD in Earthquake Engineering from SVNIT Surat. Also, had a special training on earthquake-resistant design. Sir has published more than 70 technical papers in national, international conferences and journals. Presently, he is preparing 18 episodes on earthquake-resistant construction and will be telecasted on DD National Network. Also, he is developing Laboratory of Earthquake Engineering in 18 colleges with Gujarat State Disaster Management Authority. Various membership of professional institutes includes Earthquake Engineering Research Institute, USA, Indian Society of Technical Education, Gujarat Institute of Civil Engineering and Architect, and many more. Sir is honored with National Awards of Best Program Officer in 2017, also State and University Award of Best Program Officer of National Service Scheme for the year 2012-13, 13-14, and 16-17. Also, Sir has been the first Indian officer associated with armed force with the rank of Major became Centurion blood donor. Sir, I welcome you on behalf of Civil IPSA.
Thank you very much for the introduction, and I'm thankful to Dr. Amit Sharma, and the IPS Academy for inviting me to deliver the session. So, shall we start the session?
Yes, sir. Yes.
Yeah. So basically, today's my session is on advancement in earthquake engineering. And can you see my screen?
Yes, sir.
Yeah. This is the last day of Atal FDP on disaster management and engineering structure safety, organized by IPS Academy Indore. And today's my topic is advancement in the earthquake engineering. I will talk about the latest advancement or advances which is taken place in earthquake engineering. So first we start with the disasters. We came across lots of disasters, and during this training program, you will be given many lectures on different disasters. And so we talk about the earthquake, we talk about cyclone, we talk about flood, we talk about fire, we talk about landslide, liquefaction, tsunami. So these are the disasters. We can list out either they are man or the natural, right? And most of the time we are saying that the earthquake is a natural disaster, right? But if you look at suppose if an earthquake hits your region, then exactly what you will do. So when earthquake hits your region, you will come out of your houses, or your offices, of your structures. So you try to come out of your building. What is the reason behind it? The reason behind it is that we have a fear in our mind that the building will collapse, uh, and the casualty may happen. Where you go? You go to the open space. When you go to the open space, this open space is nothing but it's a nature. So if we say earthquake is a natural disaster, definitely you will not approach nature. Just imagine if the cyclone hits the region, what exactly you will do? When cyclone hits the region, then you will remain in your house, right? Because cyclone is a natural disaster, and you will take some time that cyclone will subside, and then you move out, right? Because cyclone is a natural disaster. But in case of earthquake disaster basically it is not a natural disaster. Earthquake is a natural threat, right? And when you go to the open space, you feel comfortable. Why you feel comfortable? The reason is uh, uh, you don't have a fear in your mind that your building will collapse there, right? So basically, because of collapse of the unsafe structures, this is happening, right? And who constructed these structures? We civil engineers have constructed, right? So basically, I'm always saying that earthquake do not kill, but the unsafe buildings do. And therefore, you just imagine if all the buildings are safe, then nothing is going to happen. You will remain in your house, right? So therefore, we are saying that earthquake is not a man-made disaster. Earthquake is a earthquake is a natural threat. Earthquake is not a natural disaster. It's a man-made disaster. So therefore, we always say the solution lies in the building, not in the earthquakes. So we have to make buildings such a way that it remains safe during earthquake. Now, when you compare the India and you compare the China, I at this moment I want to share my experience. Uh, I was there in the Japan, and I was attending a session, and I was on the 9th floor, and suddenly the area was hit by the earthquake. Right at that moment, like we Indians have a fresh memory of 2001 earthquake, right? So we have that memory in our mind. So when we feel that the earthquake was there, then suddenly the delegates from India start running towards the stair, right? But if you look at the Japanese people stay there at their places, and they simply balance themselves. And once the earthquake was over, you see, nobody were running during earthquake. When earthquake was over, they were clapping. The earthquake is over, right? Because they know from the 9th floor you cannot reach to the ground floor, and you cannot go to the open space. And the most important part is Japanese people. They have faith in their building because they are implementing the building bylaws and the norms for the earthquake very strictly, right? So we have to basically develop understanding that earthquake do not kill, but the unsafe buildings do. So we have to focus on the building. We have to make our building safe, and we have to reduce the casualty, right? And if you look at all the disaster, then you will find that among all the disaster, maximum loss of life, maximum economic loss is observed during earthquake, and that therefore it is very important for us. And the why the maximum fatality is observed? If you look at you see here the earthquakes, the red part is showing the earthquake, green is a cyclone, uh, and the blue part or sky blue is basically flood, and the remaining is the other disaster. Now if you look at the flood, the loss of life is very less, but the economic loss is very high, right? Suppose if you look at this chart, then you find that earthquake is having the maximum fatalities among all disasters. At the same time, economic loss is the highest. If you look at the cyclone, the loss of life is high, and the economic loss is also high. But in case of flood, loss of life is less and economic loss is high. The reason is we can predict flood. We are able to predict flood, and therefore what happens before any event happens, the people go to the safer places. But at the same time, their property cannot be prevented from the flood. So their property may be affected. So economic loss is higher, but the loss of life is less. Suppose if you are able to predict earthquake, then definitely we can reduce the loss of life. People are working on, but we don't have any significant success right now, and therefore loss of life is very high as far as earthquake engineering is concerned. And right now we are working in this area to predict the earthquake. Right now we have done a significant advancement as far as the prediction of cyclone is concerned. We are predicting cyclone quite effectively. So loss of life is reduced as far as cyclone is concerned. But right now we are not able to predict earthquake, and therefore loss of life is very high. And if you compare the loss of life, suppose if I'm taking the earthquake of 2001, we have lost almost 14,000 people, 15,000 or 14,000 people during Bhuj earthquake. Same type of earthquake was taken place in America in 2003. After 2 years of the Bhuj earthquake, only 50 people died. Just imagine. So these countries are well prepared. America, Japan, New Zealand, they have worked excellently well. They are knowing, Japan is knowing they are situated on ring of fire. They are knowing the frequency of earthquake is very high. But as far as India is concerned, our priority is something different right now. Right now, we are basically a developing country, and our priority is something different. So our focus is not on this right now, and therefore the loss of life is very high. And at the same time, we are not applying our building bylaws very strictly. Once there is a political will, once there is a policy that this bylaws and the earthquake safety rules will be followed, all the codes and everything will be followed strictly, religiously, then we can make the safe houses, right? So these are some disasters which are the secondary disasters due to the earthquake, you can say. Tsunami is a disaster due to the earthquake. Liquefaction, which is taken place, fire, landslide, flood, and nuclear disaster, right? I'm not going to talk much about it, but we come to the main part. If you look at the global occurrence of the earthquake, you feel that the big earthquakes are rare, moderate earthquakes are occasional, and small earthquakes are frequent. If you look at this table, then you find that we are expecting basically one great earthquake per year, right? Great earthquake means whose magnitude is more than 8 or more than 8. We are expecting 7 to 7.9 earthquake, almost 18 earthquakes we are expecting in a year. 6 to 6.9, we are expecting almost 120 earthquakes, right? These are the significant earthquakes. So in a year, we are expecting almost 140 earthquakes, whose magnitude is more than 6. If you talk about the moderate earthquakes, I'm talking about these earthquakes. These earthquakes, almost 7,000 earthquakes. It means almost you have 20 earthquakes per day, right? And if you go for a very small earthquakes here, you find that 49,000 earthquakes, 3 to 3.9 magnitude. And if I'm talking about the magnitude less than 3, it is 9,000 per day. Quite significant, right? But we are not worried about these earthquakes. The reason is the amount of energy released in these earthquakes is very less, and our structures are able to absorb that energy, and therefore we are not worried about the small earthquakes. We are not worried about much. We are not much worried about the moderate earthquakes, but we are worried about these earthquakes whose magnitude is more than 6. So basically, we can say we can conclude from the global occurrence of earthquake that big earthquakes are rare, moderate earthquakes are occasional, and small earthquakes are frequent. Suppose if I'm taking a very simple example, when we design our structures for a certain period of life. Right? For example, we design our structures for 100 years, right? 100 years. Now I'm taking a very simple example of a building located in Bhuj region of Gujarat, right? I'm talking about the Bhuj earthquake or the Kutch region. Kutch is in the Gujarat, right? And I'm talking about the two buildings or two structures. One is constructed in 1818, and another is 1820. We are knowing that there was a great earthquake. There was a great earthquake in Kutch in 1819, and as far as this region is concerned, the next earthquake was taken place in 1956, Anjar, right? So the gap between the two successive earthquakes in a particular region was almost 130, 140 years, right? Now we are taking the two structures. One is constructed in 1818, another is constructed in 1820, right? Now I'm assuming a life of 100 years, right? So the first structure which is constructed in 1818, it will expire in 1918, right? Now if you look at how many earthquakes it is observed, we are knowing that the earthquake was taken place in 1819. It means the building which is constructed in 1818 had observed a great earthquake, immediately after its construction, right? So if we ask this building what should we do as far as earthquake design is concerned, then this building will say that you have to go for the earthquake proof design. Earthquake proof means no damage condition, no damage. It is safe, but this is uneconomical because the sections are very large. Our structural elements are much bigger. So as far as our structural element and cost is concerned, our structure become uneconomical. Suppose I'm taking the another structure. The another structure is constructed in 1820, right? So this structure will expire in 1920. How many earthquakes this is observed? Because we are knowing that we had an earthquake in 1819 and the next earthquake was in 1956. So during the life of this structure has not seen any earthquake, right? So if we ask this building that what should we do, the building is not knowing about earthquake. So building will say that okay, there's no need of designing the structure for earthquake because this building has not observed any earthquake. But if we do this, then when earthquake comes, because we are not sure whether earthquake will come or not, but when earthquake will come, it will also collapse, and it is unsafe. So as a civil engineer, we never design unsafe structures, right? So as far as the first structure is concerned, first structure is saying that you go for the design which will not observe damage. Another is saying that no need to design structures for earthquake. You see, now we are confused. Should we go for the earthquake proof design? Now earthquake proof design, if I'm sure that if earthquake is going to taken place during the life of the structure, if my structure is going to see at least 2, 3, 4 earthquakes during the life, then definitely I can go for earthquake proof structures. I can go and I make my structure uneconomical. But there is no surety. Basically, earthquake is not a sure event. As earthquake is not a sure event, so we take a chances. What chances we are taking? We are going for earthquake resistant design. What is earthquake resistant design? We are saying that we are not going to design for the full level of earthquake force. We are not going to design. So if you look at this, then you see this is the maximum force which is coming on your structure, but we are not designing for this full load. What we do, we are relying on the ductility of the structures. We reduce the force. We rely on the redundancy. We rely on overstrength, and ultimately we design our structure for a force which is quite less as compared to the maximum force which is acting on your structure. So you see, therefore I am saying that we, as far as earthquake design is concerned, we are going for earthquake resistant design. What is earthquake resistant design? Earthquake resistant design is we are designing our structure for the certain percentage of the maximum force We are not designing our structure for maximum force which is acting on the structure, right? So basically, when we go for the dead load and live load design, it is a strength-based design. Strength-based design means we load coming on your structure is 100 kilonewton, then we use the factor of safety 1.5. So we design our structure for 150 kilonewton. But against that, when we design our structure for earthquake, we are not designing for full force. It means if the earthquake force coming on your structure is 100 kilonewton, we are not designing for 100. We design our force, our structure for maybe 20 kilonewton force or 30 kilonewton force, means 20% force or 30% force, right? Now the question will, how our building will survive, right? So again, I'm saying that we are not designing our structure for the maximum force which is acting because of earthquake, right? We are designing for much lesser force. Much lesser force means this is a design force which is maybe a 20% or 30% of the actual earthquake force which is acting, right? But during earthquake, you see, just imagine what happens during earthquake. During earthquake, the rupture of rock mass, big rock mass is taken place, right? When there is a rupture, the huge amount of energy will release, and this energy is basically released during the earthquake, and it travels in form of waves, right? And these waves will shake the foundation, right? It means some of the energy is entering into your building, and therefore earthquake resistant design is concerned, we have to absorb this energy. Right? Now we can absorb energy by two ways. We design for the maximum force, and our structure will remain linearly elastic, or we design for the last level of the force, and the most important part is we rely on ductility. Ductility means, what is ductility? Ductility means we are relying on the inelastic deformation after yielding, right? Now you see, if you look at this graph of load versus deformation, then the area under the curve will give you the amount of energy absorbed, right? So we have to absorb the earthquake energy. So earthquake resistant design basically depends on the energy absorption of a particular structure. So we have to absorb the earthquake energy. So we are not designing for the maximum earthquake force, but we are designing for maybe 20% or 30% of the maximum force due to earthquake. But we rely on the ductility. Ductility means the area. Ductility means the deformation after yielding. This is an inelastic deformation, right? Inelastic deformation means ductility where the damage is taken place. Right? Inelastic deformation means if your structure is elastic, then once it will vibrate and it will come back to original position. But when your structure is entering into inelastic range, it will not come back to its original position, and therefore it absorbs damage if it enters into inelastic zone. It means your structure may absorb cracks, and this is generally we observe during the big earthquakes, right? So we are saying that is not a sure event, and therefore what we are doing, we are not going for earthquake proof design, we are going for earthquake resistant design. And in earthquake resistant design, damage is expected, but collapse is not allowed, right? So basically we are not compromising as far as the safety of the structure is concerned, right? We are saying that if earthquake will come, my structure may get damaged. If big earthquake will come, my structure will get damaged, but it is not going to observe any collapse. This is the most important part, right? So when we design for the low level of earthquake force, the structure will become economical, right? So this is the only philosophy in which a damage is expected, earthquake resistant design philosophy. Now you see here we are taking the chance. Means what chance we are taking? Suppose we take this building, the building which is constructed 1820, which was supposed to expire in 1920, but this structure has not observed any earthquake during. So we have not gone for earthquake proof design, we have gone for earthquake resistant design. So we are saving the money here, right? Now imagine how many buildings constructed during this 100 years, right? So definitely there is lot of money is saved. The economy is basically, but you see, so we have to go for earthquake resistant design. Earthquake resistant design means damage is expected. Suppose if we cannot say my building will not see any earthquake. If we take the case of Gujarat earthquake, we had an earthquake in 1819, right? The next earthquake was in 2001. Means almost the gap is 180 years between the two big earthquakes, right? Now, if I imagine that now next earthquake is going to come after 180 years, no, that is not correct. The whole earthquake engineering is based on probability. The probability means earthquake may come tomorrow morning also. You have to ready for that. But the probability of having big earthquake next morning is very less, right? And therefore we are taking the chances. We are making our structure safe, but at the same time we are expecting damage. Damage means what? If earthquake will come, damage is taken place, and then we have to retrofit that building or we have to repair that building. So we have to imagine that if earthquake will come, then a big earthquake will come, then we have to repair or retrofit our structure. That is to be required. So this is what the philosophy is. When in case of a minor earthquake, we are expecting damage in non-structural members, not in the structural members. In moderate shaking, we are expecting some damage in the structural member and heavy damage in non-structural member. But in case of a strong shaking, we are expecting a very heavy damage in the structural members. Remember, we are expecting more damage in the structural members. But collapse is not allowed. This is the bottom line. Collapse is not allowed under any circumstances. Remember, this is the bottom line. So if you look at the philosophy of earthquake design, it simply says that under minor but frequent shaking, so we generally observe non-structural damage or structural damage. Structural damage means the members which transfer loads of structure, which are designed to resist loads. Non-structural member means they are used for the functional purpose, right? Like if I am talking about an RCC structure, in RCC, the load of the slab will transfer to the beam will transfer load to the beam column joint, then column, then foundation, and to the soil. The non-structural members, they are the walls. Generally, the walls are used for the functional purpose. They are infill walls, right? The purpose is not that they will take the load, right? So the under minor shaking, which is frequent, so we expect a repairable damage in the non-structural member. Remember, non-structural member, but there's no damage in the structural member. But when the earthquake of magnitude maybe 4 to 6 will come, then there may be a damage in the non-structural member and repairable damage in the structural member. But under strong shaking like Bhuj earthquake or Japan earthquake or any big earthquake taken place, then there is a heavy damage in this non-structural member and the structural member. But the bottom line is no collapse. This is very important. Collapse should not be there, right? This is the bottom line. So the difference between the earthquake-proof design and earthquake-resistant design is that in earthquake-proof design, we design our structure for the maximum expected force and for the no damage condition. Now here we rely on elastic deformation. It is safe, but it is uneconomical, right? Here ductility is not required. But earthquake-resistant design, we design for maybe a 20%, 30% force, but we rely on elastic deformation. We design our structure such that it will absorb the earthquake energy, right? So we are relying on elastic deformation. It means ductility. It means damage. Ductility definitely related with the damage. So here, your structure is basically safe. Remember, structure is safe, but at the same time, it is economical. And only thing is that you have to be ready for the retrofitting in case of major earthquakes. That's all, right? So this is what the preliminary things we just discussed. And if you look at the actual scenario, actually what is happening, if you look at any earthquake taken place, whether it is in developed country or developing country, buildings are collapsing, right? In developing country, more buildings will collapse. In developed country, less building will collapse. In developing country, number of deaths will be high as compared to the number of deaths also in developed country, right? This is generally we observe, whether it's a 1994 Northridge earthquake, 1995 Kobe earthquake of Japan, or a 1999 Turkey earthquake, or 2001 Bhuj earthquake. Everywhere we have seen the devastation. It is more in case of like Turkey and the India. If you look at the Japan in 1995, most of the bridges are affected, and in 1994 Northridge earthquake, it affects, but it affects quite less as compared to the India, right? So now we come to our main topic. The earthquakes are uncontrollable. Basically, this is the fact. We cannot control earthquake, right? We cannot prevent earthquake to happen, and at the same time, seismicity is increased. So basically, we have to design our structure such that capacity should be more than the demand. Then your structure remains safe, right? So we are knowing the earthquake induces the force, that is mass into acceleration, right? So if the value of F will increase, earthquake force will increase, then we have to increase the strength of our structure. We have to design our structure for high level, right? So we have to increase the capacity, right? We have to increase the capacity. So capacity should be more than demand, right? So there are two things. Again, I'm saying capacity means whether we go for the elastic design or inelastic. We rely on elastic deformation or inelastic deformation, which is more important, right? So here we basically rely on inelastic deformation, and here we are not observing the strength-based design, but we rely on the ductility. It means the area under the curve. The area under the curve means, I'm talking about this area. Remember, this is the area. If you allow the inelastic deformation, this area under the curve will be much higher, more ductile your structure, then the larger will be the energy absorption, and definitely this will give you a safe structure. But the ductility is high, it means inelastic deformation is high, it means damage is high. So ductility is indirectly related with the damage. Remember, this is very important. We calculate the forces, right, like this as far as Indian code is concerned, right? So we calculate the design lateral force at each floor level, and then we design our columns or our supporting system for that, right? Now, basically, this the earthquake force is acting in all the three directions, means two horizontal directions and one vertical direction. Now, which component is important for us? You see, we are designing our structure for dead load and live load. When we design our structure for dead load and live load, the factor of safety what we are using is 1.5, right? It means the 100 kilonewton load is coming on your structure, we design for 150 kilonewton, right? So suppose if earthquake will come and it is having a vertical acceleration, it means earthquake force will act in the vertical direction, right? Then this factor of safety will take care. Of this additional earthquake force which is acting on the structure, right? But when your structure is located near epicenter, this vertical acceleration is very high, so you have to design your structure for vertical acceleration. But if your structure is located away from the epicenter, there is, I think, the factor of safety we are using for dead load and live load design will take care the earthquake force also. So the important part is the lateral force. Basically, the lateral force which is acting on the structure. This is the lateral force which is acting on your structure, and your structure is uncomfortable against this lateral force. What is the reason? The reason is this force is acting in the lateral direction, and you have to transfer this force in this vertical direction, right? So the important part is, like, we have to transfer horizontal load in vertical direction, and therefore your structure is uncomfortable. You just imagine you are holding bag, right? And you are holding your bag on your head, you are comfortable, right? But suppose you are holding on your bag by keeping your hand in 90 degree with your body, right? Then you are uncomfortable because we are transferring a force in a very awkward way, right? So here the same thing. This force is acting in the lateral direction. We have to transfer in the vertical direction. Therefore, your structure is not comfortable because our load transfer member is located in the vertical direction, right? Now, which are the load which is this with the lateral load resisting systems. Generally, we rely on the shear walls, bracing systems, MR frames, and tubes. Right. So these are the things we normally use. These are the normal lateral load resisting systems. Right. The shear. What is shear wall? The shear wall, basically, you see, it is a structural wall. Actually, it is a structural wall. But we are saying it is we are saying a shear wall. Why shear wall? The structural wall may be a shear wall or the flexural wall. But the shear wall means this is the wall which attracts or is it's governed by the design of this wall is governed by the shear deformation, right? Not because of flexural deformation. In most of the cases, if we say if you put a shear wall means it's the vertical, the concrete wall in the vertical direction of the reinforcement, right? So we talk about the shear wall. The shear wall is a wall designed to resist the lateral force acting in its own plane, and the shear deformation is the main thing, right? The shear deformation, we are designing for the shear deformation, right? Flexural deformation is not governing, shear deformation is governing. So this is the reinforcement of the shear wall, right? So what exactly we are doing? We are most of the time we are putting the shear wall between the two columns, right? So that at the end we have a larger axial stress which is taken care by the columns, right? So the shear wall between the columns is quite efficient. If you don't find the column at the end, then we are generally providing boundary element, right? This you are knowing. I'm not going to discuss that part, but this is a shear wall reinforcement for the shear wall. You can look at the shear wall, how it is constructed after the earthquake. You see here, this structure was damaged due to the earthquake, and then at the later stage they have introduced a shear wall in existing structure, right? So you have to be very careful that this shear wall must be connected with the columns and the beams correctly. Then and then load transfer will take place. Otherwise, it will not become effective. The bracing system. The bracing system can be used to stop building swaying over, right? Now, generally the bracing is provided in the steel structures, right? In the concrete structures, we are providing shear walls. The purpose of this, both the things, either bracing or shear wall, is to increase the stiffness, and it will make your structure stiff. And when we are structured, because we are knowing that the earthquake load distribution is as per the stiffness of the vertical element, right? We try to prevent the larger deformation, right? So the bracing systems are provided, and the bracing system where the members are either in tension or compression, you can see here, this is a bracing system which is provided, right? These are the bracing system. You see, earthquake force is acting in the lateral direction, and we are providing an element which is inclined. So this inclined member will transfer earthquake lateral force much better as compared to the vertical member, right? So this is a bracing system. We have a special concentrically placed frame or eccentrically placed frame, depends. So we are saying that earthquakes are natural, that we already, and as far as the effect of earthquake is concerned, we have to control the damage in the structure. We have to control the consequences, right? Because of our technological advancement. Right. Okay. If you look at the recent trends, basically we are going for the very high-rise structure, means multi-story buildings, and this is the equation is any inertia force plus damping force plus stiffness force, right? This is the case of free damp vibration, right? Now, if you want to control the excessive vibration, if you want to reduce the excessive vibrations, then generally we increase the stiffness, right? We increase the stiffness, right? And correspondingly, the mass may increase, and generally it is not feasible for the tall structures. So basically, to reduce the excessive vibration, we go for the reduction. We switch over to the damping, right? If more damping, it will absorb more energy, right? More energy. So basically, if you want to control the vibration, we have three parameters: mass, damping, and stiffness. You can reduce the mass because we are knowing earthquake force is mass into acceleration. If you reduce the mass, earthquake force will reduce. So if you make your structure lightweight, it is good. Then earthquake force will reduce. The second part is like you increase the stiffness. You increase the stiffness, the deformation may be controlled. But when you increase the stiffness, the size of the vertical member will become very high. So again, we have to control the sizes of the structure element. And the third element is the damping. The damping is very important, and you have to increase the damping. Like if we talk about the steel structures, we assume 2% damping. If it is a RCC structure, it is 5% damping. If it is a masonry, it is around 8%. This is what we are assuming. It is nearby, right? So the masonry structure absorbs more energy as compared to the steel structures. 2% damping in steel and 8% in masonry, or 5% in RCC, 2% in steel. So energy absorbed by the RCC structure is definitely higher than the steel structures, right? So this damping is very important. And again, I'm saying, as far as the earthquake resistant design is concerned, our focus should be on absorbing the energy. So damping will play definitely important role, right? So dissipation of the energy is required, and to dissipate the large amount of energy, we have to make certain extra arrangement, and this is known as a structural control devices. This is structural control devices, okay, structure control systems, right? That is to be required. So what are the structural controls? The structural controls means incorporating the external element to the structure to control the dynamic response, right? We are introducing new structural components, in our structures, which will control the dynamic response. Means when earthquake will come, it will control the vibrations, right? And which type of structural controls we are talking about? There are different types of structural controls, right? Structural controls are different type. Is a passive control. It is a active or semi-active control, or hybrid control. Am I audible? Is it going fine?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir. No problem.
Yeah. So basically, if you feel that if I'm going with the pace, then please tell me. I will reduce the delivery of my session, right? I reduce. So structural controls. The structural controls, we talk about the passive control, active or semi-active control, or hybrid control. Hybrid control means is a combination of active and passive. And in passive control, we talk about the seismic isolation or base isolation. We are talking about energy dissipation devices. This is we are going to talk about. We talk about the mass dampers, right? So we are going to discuss this part now. So types of structure controls, we said passive control, active control, or semi-active control, or hybrid control. First, we talk about the passive control system. What is passive control? Simply, you can say that we are introducing certain elements in our structure which are not active during the normal circumstances. But when earthquake will come, it become active. So it remain passive in your system. When dead load and live load is acting, it remain passive. But when the lateral force will come, it start reacting to it, right? So that is known as a passive control system. So this control is neither powered or not smart. Means you don't require the power supply, anything else, right? So we are introducing certain elements in our structure which remain inert during the normal circumstances, during the dead load and live load. But when the lateral load will come, these elements will become active, right? And we are talking about we are playing with the different, you see, we are playing with the damping and stiffness, right? Basically, we want to control the vibration. So the passive control, it requires no external energy. Energy is not required. We are putting the structure elements, and we have to select a structure element, or we have to introduce an element which is according to the situation, right? We'll see that what exactly it is. Okay. So first we talk about the base isolation system. Base isolation system. What is base isolation? You see, again we go to the behavior of our structures during earthquake. During earthquake, what is happening? During earthquake, energy will release. This energy will travel in form of waves. These waves will shake the foundation. Now, when the waves will shake the foundation, your structure, basically your structure is at rest. And as per the Newton's law, body at rest will try to remain at rest. So it will exhibit the inertia force. And this inertia force is the earthquake force. So it will exhibit the inertia force. So when earthquake shakes the foundation, your building will vibrate in horizontal and vertical direction. So here we are talking about the horizontal direction, lateral direction, right? So what is happening? This energy is entering into your building, and when your energy is entering into your building, your structural components are undergo deformation, and this structural component is having limited deformability. It can deform up to certain limit. If it deforms more than that, damage will be observed, right? And therefore, what we are doing, we are introducing the isolation system. We are providing a isolation system between the foundation and the superstructure. It means when the earthquake will shake the foundation, then your superstructure almost behaves like a rigid body, and most of the deformation will be taken by the base isolator. And this is one of the base isolator. You see, this is the base isolator, right? These are the base isolators. So in such a way that the lateral deformation is allowed, right? So what is actually base isolation? That we'll discuss, right? So certain if you talk about high seismic zones, then we can observe acceleration more than 1G, right? And designing our structures to this level of force, I think it is not easy or not cheap. And therefore, you see, as far as our code is concerned, the code basically uses the ductility to reduce the capacity and to achieve the capacity, right? So as far as our code is concerned, is rely on ductility. Which code I'm talking about? I'm talking about the IS code, IS 1893. IS 1893 is having five parts right now. The part one is for the building. I'm talking about the buildings right now. I'm not going to discuss other like bridges and embankments and other. I'm not discussing right now. But the most important thing is the IS 1893 part 6 is coming. The draft code is there, and this is particularly related with the base isolation system. So India is ready for the base isolation system. Okay, so the code is already there, and maybe within a year or two, we have a code for base isolation even. So right now we are talking about, like, if you talk about the IS 1893 1 to 5 parts, basically it talk about the ductility to save our structures, right? But I told you earlier that ductility means what? Inelastic deformation. What is inelastic deformation? It is nothing but it's a damage, right? It means once a big earthquake will come, then your structure and element will absorb damage. And when your structure element will absorb damage, its capacity will reduce, and the capacity will reduce, then you have to retrofit your structural elements, right? And therefore, suppose if we want to prevent our structural element to undergo damage, then the solution of this is basically a base isolation system, right? So what base isolation system will do? We are not increasing the capacity, but at the same, what exactly we are doing? We are reducing the demand. This is very important. Base isolation is reducing the demand rather than increase the capacity, right? So this is very important. Again, I'm saying, for earthquake, we are designing our structures to absorb. Basically, we are designing structures such that it will absorb the earthquake energy. Our earthquake design is not a strength-based design. Remember, again, I'm repeating. Our earthquake design is basically based on energy absorption, right? And here, the base isolators are reducing the demand rather than the capacity. What is isolation? The isolation means a state of being separated. So here the structure is separated from the foundation. That is the isolation. The concept in isolation is to reduce the fundamental frequency. What exactly we are doing? I will show you. This is important, right? Now here you can see. Suppose your structure. This is the graph of SA by G, means acceleration versus the natural period of the building, right? Acceleration was the natural period of the building. Now, if your structure is suppose falling somewhere here, it means the spectral acceleration is very high, right? So what we do, we provide the base isolation, and what the base isolation will do? Base isolation will increase the natural period of the building. Natural period. It means you are designing such a way that this natural period will increase, right? Natural period will increase. And if it will increase, then the acceleration, you see here, this is the acceleration, which is reduced quite significantly by this, right? So by introducing the isolators, we are increasing the natural period, reducing the frequency, right? This is what we are doing. So the main thing as far as isolation is concerned, we are designing in such a way that the frequency of structure is something different and frequency of isolator is something different. So we are separating. We are separating the frequencies, right? This is very important. Okay, so what is the purpose of base isolation? You see, we know that hospital buildings, school buildings, fire stations, institute building, there are TV stations, or these are very, very important buildings. And these buildings are known as the lifeline structures. And this structure should remain working during the major earthquake event, right? It should remain functional after the earthquake. This is important, and therefore this base isolation is important. So reduction in seismic force is very important for us. Here, as far as base isolation is concerned, it reduces the seismic force as compared to the conventional structures, and it is said that almost 60 to 70% force can be reduced using the base isolations. It means the demand is reduced, right? Demand is reduced. So an objective is to protect the structures from severe earthquakes during the strong shaking, right? Now here, if you look at this, the concept is when there is no control, this is the response, right? Seismic response. But when you use the base isolator, the response will come down, right? Response will come down, right? And the energy level will reduce. Now here you can see how the structure is vibrating. This is very important. Here you can have an interstory drift, right? In as far as this is concerned, in this you have an interstory drift, while here the interstory drift is gone. It is not there at all, right? So this is the advantage of the isolators, right? Again, you can see in the first case, you have an isolator here, right? And because of the isolator, the superstructure almost having a rigid deformations. While in case of this, there is in our normal structures, if you look at the interstory drift, I think you can observe these two parts. Just look at this. This is very important. Okay, so basically, what is isolator? It consists of a setting device which is flexible in horizontal direction and very stiff in vertical direction, because we have to make this isolator in such a way that it will transfer the dead load and live load quite effectively, right? Because they are acting in the vertical direction, so they must be stiff in the vertical direction. But earthquake lateral force due to earthquake is acting in horizontal direction, so it must be flexible. So we allow the deformation in horizontal direction. right? And it is located between the foundation and the main structure. When you introduce the isolator, it will produce a new mode of vibration, right? And the most important part, I told you that new mode means there's an increase in the fundamental natural period of the building, right? And the interstory drift is reduced, right? Interstory drift is reduced. Right? This is what we have discussed, right? By introducing isolator, we are elongating the natural period of the structure, and from this graph it is quite evident that the response SA by G will reduce drastically, right? So what are the advantages of base isolation? It will basically you are separating the frequencies. What is resonance? Resonance means the frequency of earthquake matches with the frequency of structure, then the resonance will be there. Resonance means your structure is going to give larger response. Simple. That if you like ice cream and if I offer you ice cream, then your response will be high, right? Same way, the frequency of structure is something, and earthquake supplies the same frequency. If earthquake supplies the same frequency, your building will respond greatly, right? And by using this base isolator, we are separating the frequencies, and so it will avoid the resonance. Now, as I told you, the natural period will increase. You see, natural period is increasing, right? It means SA by G value is reducing from this point to this point, right? It is reducing when you go for the isolation. It reduces the interstory drift, right? Interstory deflections are reduced. Ductility requirement. Now, if you go for the isolators, then the ductility requirement will be less, and it reduces torsion effect to certain level. I'm saying. Basic element of flexible mounting or energy dissipator, and we'll see that part. Basically, the type of isolation system. We have different type of systems. We have elastomeric based is a HDRB or LRB, means high damping rubber bearings or lead rubber bearings. Isolation system on sliding base, spring type systems of slip pile isolation or rocking systems. Various types of isolation systems are available. So we will see this. This is a system which is a very flexible in horizontal direction, capable of transferring vertical. So first we talk about the elastomeric bearing, which is the most popular right now. Is consist of the thin rubber and a steel plates. If you look at this the rubber layers are inserted between the steel plates, right? What the steel plate will do? The steel plate will give you the stiffness in the vertical direction. It will transfer the vertical load and prevent bulging of the rubber, right? It is literally constrained the rubber sheets. And what the rubber will do when you introduce the rubber, it allows the horizontal flexibility, right? So here you can see this is the system. This is basically a system, and here how it is executed, right? So here we have to keep in mind that the steel plate will transfer, but at the same time you have to prevent the bulging of rubber because of the vertical load, bulging of rubber may take place. So you have to literally constrain the rubber sheets. That is very important. So here you can see this is provided somewhere here to control the lateral bulging of the rubber, right? So this is the system you can see in actual sense, which is placed in the real structure. Second is the lead rubber bearing. The lead rubber bearing means we are using the rubber layers with steel plates, but at the center we are using the lead, right? In the center we are using the lead. So natural rubber, steel plate, and a lead cylindrical plug. This is providing the initial rigidity to the structure, right? That is the reason we are introducing, and you can see the better view. These are the steel plates and the rubber steel plates and rubber here, and the central part, which is the lead rubber bearing, right? We have the different. There's like sliding isolation system. In sliding isolation system, you can see here This is the base plate, and this is the column base, and here this is a slider. Now this is this surface on which it will slide, right? So a layer with a definite coefficient friction with will limit the acceleration and forces. But here no restoring force will be there. So restoring force is given by combination of the elastomeric bearing and also by the friction management systems. The isolation in real building. If you look at the Bhuj hospital, right? You'll be surprised that in 2001, Bhuj earthquake, the hospital building, government hospital in Bhuj was collapsed. And then at that time, the Vajpayee government was there, and they have sanctioned 100 crore rupees for the hospital. And a new hospital building was constructed in Bhuj, and the cost of that hospital building was 100 crores, and out of these 100 crores, 10 crore was the cost of base isolator. You see, 10% is the cost, which is quite high. The reason is India is basically using the isolators as far as this building is concerned from the New Zealand, and we are not actually using it effectively. When it will come in the routine use, the cost of isolator may reduce. But as far as India is concerned, we have few buildings which is having such isolation systems. Right now we have maybe 8 to 10 structures in 8 to 10 structures which are isolated in India. So the Bhuj was the first big structure which was isolated. And before that, I tell you, before that, in 1993, there was a Latur earthquake. Latur is in Maharashtra. It is known as a Kilari. So Latur earthquake, the first building was introduced in India with a base isolation technique, right? And today around, as far as world is concerned, we have more than 1,000 buildings in the world which is isolated, right? So which is a very effective technique, and the performance of this building observed wonderful during the earthquake, and they perform excellently well, right? Because your superstructure is protected. Generally no damage will be observed in the superstructure, and it is possible that after the earthquake you have to change the isolator. Maybe if a larger deformation is taken place, you have to change the isolator, and then again your structure should structure remain functional. Now this is the Bhuj hospital. Looks very beautiful and nicely executed by the L&T. Right. This Bhuj hospital is mounted on lead rubber bearings. It is manufactured and tested by the Robinson Seismic Limited and designed by the Holmes Consulting Group and Dunning Thornton. Right. So this is the Foothill Communities Law and Justice Center. It's basically a 4-story eccentrically braced frame. This is the first seismically isolated. This building is first in the world which is isolated. The total cost was almost 210 crores, means $30 million, right? And it is mounted on 98 high damping elastomeric bearings, HDLBs, right? We go to the next part. The next part is the tune mass dampers. Tune mass dampers. What is tune mass dampers? Basically, we are adding certain mass to our structure. We have our main structure. The main structure is having certain mass, right? Now we are knowing that what is the frequency? Frequency is basically 1/2 pi square root of K by M, right? So it depends on basically on stiffness and mass. Again, I'm repeating, the frequency is nothing but 1/2 pi square root of K by M. It depends on stiffness and mass, right? So your main structure is having certain mass. So you are introducing us. Suppose if you play with the mass, additional mass, then you can change the frequency of your structure, right? So here, what exactly we are doing? We are introducing certain mass in the system, additional mass, And this natural period of the added mass, it should be close to the fundamental natural period. So it is also tuned mass temper, right? What is the purpose of tuned mass temper? Is to reduce the horizontal vibrations of a tall and slender constructions, right? We talk about damping, right? We talk about damping. What is the damping? Damping means the amount of this capacity to absorb the energy, right? Right. It's the energy absorption capacity of the system. And what is a tuned mass damper? A tuned mass damper is a single degree of freedom oscillators that is attached to the structure for the purpose of reducing resonant vibrations. Right. What exactly the system is? You see, the system is like this. This is your main system, right? This is your structure, and you are adding certain mass to it. It is designed basically, and design the mass such a way that you are changing the frequency of your original structure, right? You are tuning that. You're tuning the mass in such a way that okay. So basically, this mass is added to the different levels, and this mass is generally kept a minimum, and the tuning when we're tuning the mass, it doesn't impact the static strength or stiffness of the base structure. This is the most important part. Oh, you see, now you can understand what actually we are doing. We have a main structure, we are introducing the additional mass, and we are to change its frequency. So whatever the predominant frequency, your structure will go to the other frequency, and they will not resonate. That is the most important part, right? So how it will works, you can see here. We are putting the additional mass. This is a sketch, and this is our original structure. We are having the certain mass and stiffness. So you see, this is the actual view, pendulum type tuned mass temper, which is provided. And basically, what is happening when the structure is vibrating in one direction, it goes in other way, and you try to reduce the vibration. If the structure is moving in right ways, then it moves in the left direction, and then it will try to control the vibration. Right. So, what exactly is when we are talking about the only this structure, there is no TMD we have. But when we provide the tuned mass temper, then the yellow, this will tell you that the response is quite reduced. This response is quite reduced. This is basically the amplitude of vibration versus the frequency graph, and you can see effect of the tuned mass temper, right? Basically, TMD is a system of spring and mass, and it is tuned exactly to the structure and a certain natural frequency of it. Due to the physical properties of the system, the damper moves out of the phase. This is what I'm saying. Your structure is moving in the towards the right, then this mass will move towards the left, and if your building is moves towards the east, it moves towards the west, and try to control the vibration, right? The tall and slender freestanding structures, which tend to excite it dangerously in one of their more shaped by the wind, right? And basically, what exactly we are doing here, we are knowing that you see, as far as if we compare the wind and earthquake, the earthquake carries different frequencies. Earthquake carries different frequencies, but we talk about the wind. Wind is acting on a structure with certain frequency. I think it's in a very narrow range, right? So when this wind also induces a lateral force, this TMD will be helpful, right? And this is basically used in the Patronus tower. Patronus tower, you can see it is introduced, and this tuned mass temper is placed, right? And again, I'm saying the same thing, that if your structure moves towards east, then this will move towards the west and try to control the vibration. Design of tuned mass temper is definitely very interesting. In Taipei 101, they have placed this system, and it is placed on 44th floor. We talk about a liquid tune mass damper. Liquid tune mass damper. We are knowing that liquid also possesses mass, right? So instead of introducing a rigid mass, we go for the liquid mass. Means a liquid. We are adding, right? So this we are placing at the top of the structure or any other place, but generally it is placed on the top of the structure. And because of the shaking, when this fluid will slosh, right? So it increases the mass, at the same time sloshing effect will be there. It is designed in such a way that it will control the vibration. Particularly this is useful when the wind vibration is there, right? Not for the earthquake. It is less effective as compared to earthquake. Wind. We talk about the various types of dampers. We talk about the viscous. We'll talk about the viscous damper, right? Friction dampers, viscoelastic damper, right? What is that? Okay. Before that, just sorry, I missed the one slide. Tuned liquid dampers uses the sloshing of the liquid in tank to dissipate the seismic energy. The advantage is low cost, ease of installation, and adjustment of the liquid frequency. This is in our hand. So these are the advantages of the tuned liquid dampers. In the Japan, first it was used, and it is in airport towers and tall structures. But the most important part is the tuned liquid dampers, where they are very effective in reducing the wind-induced responses up to 70%. This is very important, right? So these systems, tuned liquid dampers, are more effective in wind as compared to earthquake. Right. At the same time, it is also observed that tuned liquid dampers are less effective as compared to tuned mass dampers. Right? So generally, in this option, people are saying that it should be tuned mass damper should be used as compared to tuned liquid dampers. Right. We talk about the metallic yield dampers. The energy dissipation by the inelastic deformation of the metals. You see, we are introducing certain elements in the system. You see, we are using the MCB, right? Suppose if electric circuit is there, we are introducing circuit breakers, MCB. So what actually it will do? When excess supply will be there, then it breaks the path of electricity, and your system will remain safe. And with the fuse, what we are using, the fuse will sacrifice the life. The same way here we are introducing a sacrificial element. You can see this is the element we are introducing here, right? It is introduced here. This is the system. Now what exactly this is? You see, this is basically this is made up of ductile material. So during the lateral movement, the deformation of this is taken place. As it is a ductile, it will absorb energy, and the strength of this element is such that it will sacrifice the life before our structural element. So what is going to happen? Our beam and column will not observe damage, but this metallic yield dampers, it will sacrifice the life. So it works as a fuse, right? It works as a fuse, and so it basically it is a ductile, so it will absorb more energy, and this is what we need. And after the earthquake, if it gets damaged, we can replace this metallic yield dampers, and we can put a new one, right? You can see here, right? So these are the unmounted vessels. Second is the viscous fluid dampers, which is very similar to shock absorber, right? here basically the viscous fluid is there, viscous fluid, and when due to the lateral force will act on it, your structure is going to vibrate in the lateral direction, then the movement here will do along the diagonal, which is going to take place in this direction, right? So we are introducing a piston cylinder arrangement, and this is the piston, right? And here fluid is there. So when movement is taken place, this piston will move and the fluid will resist. Fluid will offer resistance to this movement, and it is having the higher damping. It will absorb the energy. So you see, we have such kind of system in our vehicles also. We have a shock absorber in our vehicles, right? It is working on the same phenomena. So we are introducing such things, so it will absorb a large amount of energy. It's a viscous damper. Viscous damper means it increases the damping of the system, right? So you can see the sizes of these dampers in the real structures. It is not small as like our vehicles, but it is much bigger, and we are designing for it, right? We have a friction dampers. Friction dampers means because of the friction, when the lateral movement will start, then we are using the element which will offer friction, right? The more friction is generated, and friction means resistance, and because of the friction, it will try to dissipate the energy, right? This is the 8-story steel building. Casino of Montreal was rehabilitated, right? In friction damper, what is happening? Yeah, we are introducing this friction damper somewhere here as a additional part, and when the movement starts, when lateral movement starts, then the whole assembly will try to move, right? And they have a friction between them, and they will absorb the energy, right? So it will introduce in like many configuration that they have. This installation may be like this, maybe like this, maybe like this. It depends. It like, suppose if we have a window here, then we can introduce like this. Suppose we have a central portion to be free, we can introduce like this. So it depends on the requirement. And if you look at this, the response of the friction damper is quite reduced as compared to a system without friction damper, right? So this is, I think, a small video, and the main advantage of the friction damper is it's having a very high energy dissipation, and they have a controllable friction force. The friction force is controllable, and compared to the reverse, like yielding of metals or friction dissipator, possesses a great capability of absorbing energy. So in yielding of metals, we have certain limitation. Here we can have a better performance, right? Disadvantages, we have a larger fatigue, and its durability also controversial, right? Here, the three systems, passive systems, are compared, like as far as isolation system, energy dissipators, or mass dampers. If we compare the cost, the energy dissipators are better, effective to resist wind. Then the mass dampers, energy dissipators, both are good. Reliability, isolation system and energy dissipators. Now, if you look at all the aspects, long durability, low cost maintenance, low cost of replacement, effective against the severe earthquake, effective when used with the flexible structures, then if you look at this, then this energy dissipators having a larger advantage. Here we have like a cost-wise, the isolation system is not good, right? It is little bit costly. Okay, so I think energy dissipators are better. Sarma sir?
Yes, sir.
Yeah, we have 10 more minutes for this
Yes,
session.
sir. Yes.
Okay.
Yes, sir.
So,
Yes.
so we take active control little like little bit fast and just will try to tell what the active control is. Okay.
Okay.
Yeah. Now the passive control. I told you what is the passive control. The passive control means the system will remain within the structure, which is generally not used during the normal circumstances. But when the earthquake will come, it become active, all right, and it will give the response. It will reduce the response of your structure. But active control, in active control, what exactly we are doing here? We are making the use of the computer, right? So what we do, we are putting the sensors here. The sensors are placed at the different level. So when the earthquake comes, then uh, uh, this sensor will sense that the earthquake occur in the region. The sensor will sense the motion and it gives the signal to the computer, and it says that earthquake of 5 magnitude, 6 magnitude, or earthquake of certain intensity is there, right? And computer will give signal to the active devices. These are the devices. Again, they are controlled by the sensors. So it gives signal that okay, it is a 6 magnitude earthquake. Now you have to generate such a response. If 5 magnitude earthquake, you have to generate this response, right? So basically, the online measurement of the forces will take place, and this is basically application of counteracting the forces. But it requires a more energy because you see. You have a continuous electric supply that is required for this. If no electric supply during the earthquake, then the whole system may fail, right? So we have we require a stable system. It requires more energy, but it is effective also. Now you can see the system in reality. It is a huge system, right? Huge system, which is made up of number of components, right? So it requires considerable amount of energy, external power, tens of kilowatts. Use measured structural responses to determine the desired control forces. It is more effective than the passive device because the ability to adapt the different loading condition. Means you see we have a sensors. Sensor will sense the deformation. It determines what is the intensity of shaking, and the corresponding response is generated. That is important, right? Uh, we generally say it's not reliable. Not reliable. It is suppose the continuous power supply is there. It is reliable, quite reliable, but not reliable because the large amount of power required for the operation may not always be available during the seismic event. This is the fact. If you don't have the supply during the earthquake, then this become uh, uh, obsolete. It means this is not required. It requires the power supplies. Otherwise, it will be useless. The cost and maintenance is significantly higher than the passive control. Passive, we talk about the mass active tune mass dampers. Here we talk about the active mass dampers, right? So it's similar to tune mass dampers, but included the actuators that is used to in position the mass at each and every instant, right? So here the actuators is used and to increase the amount of damping achieved and the operational frequency range of the device, right? It is introduced in the you see Japan is very aggressive in using the new technology. They are keep on experimenting the new things. As far as India is concerned, we are, I think, quite passive of using this such kind of structural controls. Even passive control is not used effectively in India. This is the approach tower in Japan. It is had used this system, right? So they use the multi-stage rubber bearing and the actuators. You can see here. Here you can have this system, and here you can see the actuator which is used to control the vibration, right? Then you have a hybrid control system. Hybrid control system, basically it is a series or parallel combination of an active or semi-active system with a passive one. So here we are mixing the active and the passive both. We are mixing that part. And what is the advantage of it? the advantage of passive system and advantage of active system, both can be combined, and we can have a better system. Right. So what exactly we do? The passive device reduces the major displacement, right? And the active system can give the final adjustment. That is the purpose behind it, right? So it will reduce displacement as well as acceleration, right? So this is a Sensugu Park Tower where the hybrid mass damper is used. You see, this is a, I think, if we see such kind of system, then we get the idea how it works, right? So here you can see this is basically your building. You are putting the passive tune mass damper here, right? So what the passive mass tune damper will, it will control the response, and any additional control, fine tuning is required, which is done by this actuator, because this passive tune mass damper don't know what is the frequency. So final adjustment will be done because this is controlled by the computer system, digital. This computer we are using in active control system. So it keep on giving the response that passive tune mass damper is controlling the deformation, and the fine tuning will be done by the active mass damper, right? So this is the combination of these two, right? So I'm not going in detail of this now because almost our time is. We have a hybrid seismic isolation system. Here we are going for control the base displacement of isolator using the active control, right? Because you see what is happening in passive control, when the shaking starts, this deformation of the various isolators are not controllable. Now here we can control through active system. So we are introducing the this active control system to control the vibrations of passive. So it is to be done, right? Semi-active controls. Basically, it cannot inject energy into the control system, but the mechanical property can be adjusted to improve the performances, right? This is what the semi-active control is. If you compare the semi-active control and the active control, then you realize that the power requirement is quite less in semi-active control because we are not injecting energy into the control system, right? So mechanical properties are adjusted to improve the performances. So if you talk about a semi-active control, the better performance than the passive control, versatility and adaptability of active devices without the large power requirements. So important part is a power requirement. So, large power requirement is not required, and its inherent stability and reliability, that is the advantage, right? We have a semi-active control variable orifice dampers. Right. We can talk about the system. Basically, this is a the electromechanical with a variable orifice valves that is to be used. Right. You see, right now we don't have the time to discuss this. Because I want to just go through the two parts, that is ER and MR. Right. These two things I want to cover. So I'm just skipping some of the portion, and yes, we come to the this part, the semi-active controllable fluid dampers, and here we have electrorheological and the magnetorheological fluid dampers, right? This is very important. These dampers with the fluid that have the ability to reversibility and change their viscosity, right? They change the viscosity. Out of this the electrorheological and damper, or the magnetorheological damper, then this ER means electrorheological damper, having the yield stress 3 to 3.5, so strength is less, and basically this fluid is greatly reduced by introducing the impurities. You see, its capacity is reduced. Suppose the impurities and it is there, it is not effective. But this MR fluid, magnetorheological fluid, is having the higher strength up to 50 to 50 to 100 kTA. Impurities will not affect, and voltage requirement is only 10 to 12 volts, right? And power requirement is less than 50 watts. So this MR fluid dampers are much better, and that is, I think, most of the time it is used. This is the Tokyo National Museum of Emerging Science and Innovation. It is designed with these systems, and this is the cable stayed bridges, which is used in China, right? They have used it, right? So now we go to the conclusion. The use of advanced technique with sound fundamental knowledge is required. When you use such kind of systems, it should not be means you see the important thing is we want a reduction in the response. This is our requirement. And suppose if you introduce anything and it will increase the response, it is of no use. So you have to use the advanced technique with the sound fundamental knowledge, right? So if you have a good knowledge, then you apply. You have to understand impact and behavior of each and every technique. Every technique is having its own advantages and disadvantages. So you have to be careful when you select any particular technique for a specific purpose. And one has to think about the financial aspect also, right? Because it is also impact the project, right? So these are the things you have to keep in mind. So sound fundamental knowledge is required, then you go for this and go through the advantage, disadvantage of each and every system, and which is the best suited for your particular project. You have to think of the financial aspect also, right? So you can see this picture. What do you mean by H2O? If you have such kind of understanding, don't use it, right? So I think it will lead to the disaster then. So you must have a good fundamental knowledge of the systems, right? So we have to begin with the end in the mind that this is my project. These are my requirements, and then I go for the such kind of systems, right? And as far as India is concerned, we have to do a lot of things. We have to climb this ladder. We haven't worked enough in the area of earthquake in the normal circumstances, and these advances are concerned. I think almost we are almost near to zero. We have not used these systems at all in India. So there is a lot of potential, I tell you. If you people will work in this area, a lot of potential is there, and I think we can do much better in future, right? So thank you very much, and I think if you have any question, we can take up.
Participants, you can ask questions. Any questions? Please unmute yourself. Sir,
Yes.
the choice of basically the damper system, will it depend upon the type of building on which we have to apply, sir?
Yes. Basically, you see, the purpose of introducing damper is to absorb the energy, right? So it depends what are the requirements of your structure, and correspondingly you have to select your system. How much amount of energy to be dissipated, that you have to thought of. Like if you require a larger energy, you can go for the friction pendulum systems or any other system you can pick according to your requirements.
Okay.
Yeah.
Any other questions?
Can you say further about energy dissipation? Since you are telling that that is a more advantage than other system, what way, sir? It is a cheap cost. Other things.
Yeah, your voice is not clear.
Example. Give some examples, sir. Energy.
Voice is not clear. I'm not getting. Hello. I'm not getting.
Maniji, can you write this question?
Yes, I can give some example for energy dissipator, which is satisfy all the needs which comes to the economical efficiency and everything. Give something.
Sir, he is trying to say that there are any such examples of dampers where we will get the what we say economy also along with the safety. Am I right?
Basically, the tune mass damper. Yeah, tune mass damper. Uh, they are quite effective. But when we talk about a uh, uh, viscous dampers, viscoelastic dampers. In case of viscoelastic dampers, the most advantageous part is that you can control the damping as well as the stiffness. Both the things you can control. So, which is more advantageous when you want to control both the things. So again, when you use the viscoelastic dampers, certain cases it is more useful as compared to the tune mass dampers, right?
Sir,
Yeah.
dampers, tune mass dampers are having more advantages. But
Yeah.
in India, why these dampers or advanced techniques are not popular?
Basically, that is the you see, if you look at our system, uh, we are not moving towards the actual safety of the structure is concerned, right? The thing is, as far as the penalty is concerned, for example, if I'm talking about the advanced country like New Zealand or USA, they go for the assessment of their buildings regularly, and they get the structural safety certificates, right? Uh, that is the one. You see, in India also, after 5 years, we have to get a structural safety certificate for our buildings. As far as Ahmedabad is concerned, that is there. And anything like if I am designing any structure as a structural engineer, after 5 years, again the owner has to take the certificate from the professional engineers, right? And if anything will happen during that or after that, then the structural engineer's role is not come to play. And you see, this is the normal thing I'm talking about. And right now we are our system is not there. Like, we don't have the code for the base isolation, we don't have the code which is pertaining to this advanced control system. We don't have the code. While if you look at the developed country, they have a specific code for all this, so they can go for it. I told you that IS 1893 part 6 is coming. Basically, it is on base isolation system. So once it will come, people start using it. Right now, in absence of this, how to encourage this, it is always a problem. We have at least, you see, in India we have only 6 to 8 base isolated buildings, right? So it is costly. So if India is having a different priority right now. Maybe the government want to take certain cases, but it is too costly, and therefore government is not taking up. And as far as you see, if we set certain examples that these are the systems or this performs very satisfactory, then people will encourage to do this, right? So we need a good codal provisions for that. And at the same time, if we increase the use, initially it is costly, but repeated use definitely means, if you use it more frequently, production is done in the India, then the cost will come down. So the two aspect will hamper right now. It's the cost and the codes availability for this particular systems. So therefore we are using it right now less. We can we can refer the foreign codes for the implementation, but right now we haven't implemented in an effective way, right?
Okay, okay, thank you.
Yeah. Yes.
If you have then you can ask it at the end of the session, next session also. Sir,
Yes.
should we come back again at 12:50 or 1?
Right now it is 12:36, right? So I
Yes,
think
sir.
we will come back around 20-minute break,
Okay, sir. Okay.
right? Yeah.
Yes, sir. So
Yeah.
12:56 we will again come back, sir.
Yeah. Yes. Yes. Okay.
Thank you, sir. Yes.
Okay. Thank you.
Thank you very much, sir.
Thank you.
So participants will again come back at 12:56.